In section 5.3, we're formalizing our idea of area with what is called the fundamental theorem of calculus. Very exciting time for us all. We are now at the fundamental theorem of calculus, which tells me that we can find the area of some function by taking the integral, and as long as I have a continuous function and it is within some prescribed region, meaning some a to an x. So for our first example, we're given that a is the area from -1 to whatever it is we call this x. So let's just do a of 3 for this first one. And our x is 3, and we're going to -1, so we're going to find the area right here. We are not given the function, we're just told what the area is. Since this is the area under the curve, this area would be -27. For the next one, we're doing f of 3, and f goes from 3 to 3, so it's the area at that point, which is 0, and we discussed that in the theorem in a previous section. For the b, I'm looking for the area from -1 all the way to 5, and so that would be all of this area. So this area that I've got has both a negative component and a positive component, so a of 5 is -27 plus 3, which would then give me -24. f of 5 begins at, 3. So beginning from here to here, and f of 5 is that area. This would just be 3, as listed right there. a of 9 goes from -1 all the way to 9. I have 3 sections of the graph here. I have a -27, a +3, and a -35 that I'm going to sum up, and for that I will get a -59. f of 9 begins at this 3 part, so I have 2 sections to this area, a +3 and a -35. This will yield -32. On to the next one. We are given a function. This f of t is 2t plus 3, and it goes from 2 to some random x out here. I can see that it's going to be a trapezoid, so if I want to find the area using geometry, I could. They give me my area function, which I could have come up with that on my own. Didn't need them to give that to me, but we're going to find area of 2. So from 2 to 2, so that's the area to point. Once again, that's a 0. We did that in a previous section. Next, we're going to do this area where x is 5. So this is going to go from 5 to 2, and our function is 2t plus 3 dt. That means that this x is 5, so if this x is 5, then my width here is a 3, and I could come up with these height points as well, because I would just plug that into the function. And because this is a regular shape, I could use just regular area formulas, but if it was an irregular shape, I couldn't do that. That's the beauty of this fundamental theorem of calculus. I'm going to use my integral. I'm going to do the antiderivative, so this would be 2t squared over 2 plus 3t. I'm going to evaluate that from 5 to 2. This cancels. This is going to be 5 squared plus 3 times 5 minus, plug in the 2 squared plus 3 times 2, and then just compute that answer. So that's 25 and 15. I think that gives me 40 minus 4 and 6 are 10. So this area is 30. Then my next thing is to find and graph the area. I think they already have that done for us, so we've got that. And we're supposed to just find what this area equals with just a regular x is what they really want me to do. So y equals, so I'm just going to integrate this just like I did before with just an x here and a 2, and then 2t plus 3 dt. I'm going to get the same thing I got before, t squared plus 3t. This time I'm going to evaluate it from x to 2. Plugging in that x, I will get x squared plus 3x. Oops, I needed 3 there. 3x minus plugging in the 2 squared plus 3 times 2. I'll get x squared plus 3x minus 10. So this would be the general formula for the area underneath this line here from 2 to any value of x. In this next section, they want you to compare that derivative to your function at the beginning. So let's just find y prime. That would be 2x plus 3. I took the derivative of that generalized area formula and I got my function back, which was what they wanted me to see. This next section gives us the fundamental theorem of calculus, and we've looked at this one already. This next part is a theorem that states what we observed with our example in the previous slide, which said that if I take the derivative of my integral, I go ahead and do the integral, and then I take the derivative of that, I'll get my function back, which was what we saw happened. And the second part of the fundamental theorem of calculus is what we've been using. Notice that capital F represents the antiderivative in this case. And I would take the antiderivative, and it's the top limit subtracted from the lower limit. You'll notice this is a notation we've been using. This right here. And these are called our limits of integration. So we're going to play with these. This is going to be some skill and drill on the fundamental theorem of calculus part 2. We're going to just be doing some computation. So I'll take the antiderivative here of 60x, that would be 60x squared over 2 using the rules that we learned in the previous section, minus 6x cubed over 3. This is all evaluated from 10 to 0. I love seeing those zeros. So reducing this a little bit, that's a 30. And this would be a 2. It's just going to plug in 30 times 10 squared minus 2 times 10 cubed. That's my first part. That's the 10. Minus, and then I'm going to do the exact same thing for the 0, except for that I know it's going to be a 0 because each of those would end up being a 0, so I'm just going to leave it. And then just doing that computation, 30 times that 100 minus 2, and then 1, 2, 3, so I get 1,000 for this answer, all done. For this one, I'll go ahead and take the antiderivative. That's a constant out front. That had to have been a cosine of x, and when I take the derivative of cosine I get negative sign, so I have to kind of backwards engineer that, and I'll leave my constant out front. And this is evaluated from 2 pi to 0, plugging in that 2 pi minus 3 times the cosine of 2 pi, and then minus 3 cosine of 0. Now the cosine of 2 pi is a 1, and the cosine of 0 is a 1. That will give me That's going to give me negative 3 plus 3, which is going to be 0. Going down here to this next one, that's kind of ugly. Don't have any quotient rule yet, so I'm just going to bust this fraction. And then I'm going to try to integrate. This would be t to the 1/2 over t, so this would actually be a t to the minus 1/2 dt. And then I'm just going to bust this thing apart. Minus integral of 1/4, 1/16, and this is going to be 1 over t, so that's going to be, I'm just going to write as 1 over t dt. This would then yield, let's see, integrating that would mean it would add 1, so this would be t to the 1/2 over this 1/2, because it would come down front, which means that is actually a 2, evaluated from 1/4, 1 over 16, minus, now what do I take the derivative of and I get 1 over t? That's a natural log. But now I have to make sure that it is not negative, even though in this case what I'm going to plug in is not going to be negative, but that's okay. I do have to, I'm just emphasizing that here. And then plugging all of these things in, this is 2, and then that would be, I'm plugging in the 1/4, so 1/4 raised to the 1/2 minus natural log of 1/4 minus, this would be 2 1/16 to the 1/2, or just take the square root of it, minus natural log of 1 over 16. Then I'm going to do some computation with that, and I'll just chunk it into my calculator, and when I do that I end up with a negative 0.8863. Now they've asked me to interpret these things geometrically, so I've got the answers to them. Now what I want to do is go get their graphs. In looking at their graphs, this one had an area of 1,000, and I could look at this and note that it was, I could say that it was 10 this way with a height of about 150. Multiply that together is 1,500. Notice that this area here, there's quite a bit that's missing, so does 1,000 sound reasonable? Yes. This next one is my cosine function. I have a very symmetric graph, the same amount in the top as I do in the bottom, therefore the area was 0. Okay, that makes sense as well. And this one, this natural log function is very close to this x-axis, and I'm asking about it in between this 1/16 and 1/4, and notice that it's just a little tiny area and it's below the x-axis, and that's what that represents. In this next example we're going to be looking at both net area and area. Let's get the net area first, is what we've been working with. Our net area is going to be, and it's from -1 to 2 of our f of x dx. They give us this function here. Oh nice, 6x, x plus 1, x minus 2 dx. You know, I don't have any rules as of yet for something like this, so I'm just going to multiply all of this out, because that would be the way I would have to do this, so I'll go ahead and write that down. Alright, don't know why they couldn't give it to me like that to begin with, but they didn't. Now we've got it, so I'm going to go ahead and integrate 6x to the 4th over 4 minus 6x cubed over 3 minus 12x squared over 2, all evaluated from 2 to -1. Pop that negative back on there. Now what I'm going to do is simplify and punch these numbers in and get an area. Okay, I got negative 27 over 2, or 13.5, whichever it is, negative 13.5, whatever it is you want to write. And the reason for this is because I have less here above than I do below. There's a bunch more below. So this is the answer to the A part. For the B part, I want the total area, meaning I want the area of the region. So I'm going to have to break this into two separate parts. I'm going to look at it from -1 to 0, and I'm going to evaluate it, fx dx, and then I'm going to evaluate the other one, but I'm not going to concern myself with the negative part because I want the total area. So I will plug this one, and then I'm going to go from 0 to 2, f of x dx, same function, so I'll get the same integral. I'll write that down. Alright, so I got those values. Now what we want is the area total. So what they want is 5/2 plus 16, because we want just the total area. So that's going to be, that's 32, so that's 37/2. And that would be my answer to 4. A nice set of 3 examples here. This one just follows my rule here, and I have a constant on the bottom and the x on the top. Beautiful. What I'm going to have is just f of x. So if I'd taken the derivative of my integral, this would be sine squared x. And that's it for that one. This one a little bit different. The x is in the lower limit, but we could just say that you know, we can flip those limits, and what ends up is I get the negative of that answer. So what I'll do is just say that I have flipped it and get the negative of that answer. So another fairly straightforward one, plugging in that x. This one, however, this next one is not as straightforward. This is not a plain x. This is some function of x. So this is some u. And I'm trying to take the derivative of this with respect to x, and I have a function inside of there. So when I take the derivative of this, I know that I'm going to have some u in there. Now, I know that the derivative of u with respect to x, du over dx equals, take the derivative of that, that would be 2x. So I could just do the same thing that I did for my regular ones here, and then my answer would just be times that 2x. So that's what I'm going to do. I'm going to say that I have the cosine of this u squared, which is what I did before, just using that fundamental theorem, times that 2x. And then replacing my u, which was x squared, I get cosine of x to the 4th times 2x. So I'll put the 2x out front because I like it better that way. And I'm done with those. Example 6, I'm supposed to find the zeros, or where my area is 0 on this line from 0 to 17. Okay, and my A begins at 0. Naturally, A of 0 is 0 because that's at point. At 4 I have a positive area. At 8 I have just as much up as I do down, so A of 8 is a 0. This wouldn't be a 0 because I got some more up, but A of 16 would be another 0 because just as many up as I do down, so I'm good with that. Okay, find the points where I have a local maxima or minima. Okay, where would I have the maximum amount of area? This right here at 4 would be a local maximum because, I'm going to write local max, because I've just added up all this area that's under that curve, and I'm getting ready to subtract some area, so I know at 4 it's the max, and then it's getting ready to get small again. There at 8 it becomes 0, So I'm going to say that's a local min. I guess I could say A of 0 be a local min too, because that was 0 there. At 12, I got another local max because while these guys canceled out, I have area that added up once again. And then A at 16 I guess would be another local min because it's gone back down to 0. Sketch the graph. At 4 it's going to be a maximum, and it's going to add up, I guess, in a similar fashion to the way it started. And then at 8 it's going to crash again, and then at 12 it's going to be max again, and then at 16, 16 is going to crash again. So there's how the area, I think, stacks up for those. Looking at this graph of the area, first up here is the function. Whoops, here's the function that's graphed, and that would be this guy here. That's one that's sitting right here. Then the next thing that's graphed is the area of that function. So let's just look at what was going on here. The area is adding up. I'm getting more and more area as I go along here to pi. That means at pi I would have the maximum area. Notice how this is the maximum point. After which I start subtracting off some areas. That's why the values here drop. And they drop until I get to this point here, and at that point then my areas start adding up again, so that's why this value starts increasing. And then of course they start decreasing again because I start having negative areas. And then this is just going to kind of settle out and barely be perceptible. Anyway, that's all for section 5.3. And if you have any questions, see me at the Collaborate, and thank you guys very much.